All right, guys, so first as we get into section 3.5, I want to give you an introduction to matrices. Maybe some of you have seen these before. So a matrix, basically the definition is a rectangular array of variables, which is kind of a strange definition. So I'm going to give you just an example so you can kind of see the way everything works. So matrices are denoted with a capital letter, so you could see anything capital A through Z marks a matrix, and we usually have these big brackets, and then inside the brackets, all of the information is organized in rows and columns. All right, so big brackets. So basically, we've just got numbers, positive numbers, negative numbers, decimals, fractions, doesn't matter. You can put absolutely anything in these matrices. Okay, so that's an example of a matrix. Like I said, you've got information organized into rows, organized into columns. So if we look this way, rows are measured horizontally like that. So this particular matrix has 3 rows, and this particular matrix has 3 columns. Columns are the vertical ones, 1, 2, 3. Okay, so then when you state the dimensions of a matrix, you always say rows by columns. So this one, for instance, is a 3 by 3 matrix. Okay, and you can have any whole number dimensions that you want. You know, it could be a 4 by 12 matrix. It could be a 1 by 1 matrix, and you could just have one little element on the inside. All right, so that's kind of an introduction to matrices. That is what we are going to be dealing with. So when we flip, this first example in the first video is going to be all about organizing data into a matrix. Because a lot of times when you're dealing with a specific context, every number in the matrix has a purpose. It's organized in such a way that the position actually makes sense to whatever data you're talking about. So in this first example, we've got a girl named Caitlin who's looking at 3 different Iowa universities, and then she's got all of this information. So like I said, it's purposefully organized in a way that makes sense. So we are going to organize the data in a matrix, columns in the order of tuition, room and board, and enrollment. So we're going to be able to set up all of that information and we can see everything. So it said columns, you want to go tuition, room and board, and then enrollment. So if the columns are being organized by the different categories here, that means the rows are going to be organized by the different universities. So we've got Iowa State, we've got University of Iowa, and then we have University of Northern Iowa. Okay, so those are going to organize our rows. So you can see if we put everything into a matrix here, we're going to have all this data. So the tuition for Iowa State is $61.60, room and board $59.58. I'm basically just copying down all of this information here. Okay, and enrollment would be the total number of people in the university. University of Iowa, $62.93 is the tuition. $72.50 is the room and board, and the enrollment is 30,409 students, and the last bit of information here is Northern Iowa. So I'm just taking all the information that's up here and just copying it down into matrix form, and then we're going to do some stuff with it. So if you read through B, C, and D, they're basically going to ask us like, okay, so all these things that we could potentially do with all the elements, would they really have any contextual application here? So part B, it says, find the average of the elements in column 1 and interpret the results. So they're asking us to look in this column right here, and when it says find the average of something, you add them all up and then divide by the total number. So the average, we're going to take 6160 plus 6293 plus 5352, and then we want to divide it by 3. That's how you find the average of anything. So we're going to take these, and I'm just going to go to a calculator page. We add 6160 plus 6293 plus 5352, and that's the grand total, and then when you divide it by 3, we get our average. So 5935 is the average. And then when it says to interpret the results, so this whole column represented the tuition for the different universities, and so the result would be the average tuition for the 3 universities. Okay, so again, you know that that column in particular represented tuition, so when you add them all together, divide by 3, that's going to give us the average tuition. Would adding the elements of the rows provide meaningful data? So if I were to add the tuition plus the room and board plus the enrollments, I'm going to go no on that one, because if we're adding these 3 values together, like adding these 2 together might make sense, because that's going to give you like a total cost that you would have to pay for your first year at that university. But then if you add the enrollment to it, these 2 values represent money and this represents people. So adding the value of money to people really doesn't make any sense. So basically what I just said, you would say, no, this doesn't make any sense because the first 2 columns are dollar amounts and the third are people. So hopefully we can see that adding a dollar amount to a number of people really isn't going to give us any sort of useful data. Okay, and then part D, would adding the elements of the third column provide meaningful data? So if we were to add these together, then yeah, I mean, if we were to add enrollment plus enrollment plus enrollment, that would give us the total number of people at these 3 universities. So yes, this gives the total enrollment at the 3 universities. Okay, so hopefully you can see now why using data inside of a matrix would be useful for us. Now we're going to learn in the next video how to do operations with matrices. All right, in the second half of 3.5, we're going to learn about 3 different algebraic operations that you can do on matrices. First is you can add, second is you can subtract, and then on the next page we're going to learn how to multiply by a scalar, which is just like a normal number. So adding and subtracting matrices, if we add and subtract 2 matrices, what we do, so say you have matrix A plus matrix B, you add them together and we get a new matrix that we literally are just going to call matrix A plus B. And so what we do is we add the corresponding elements. So like the element in the first row and first column of A gets added to the element in the first row, first column of B, and that'll be the first row, first column element in the new matrix. So it's really, really important to know that A and B must have the same dimension. If the matrices that you're trying to add do not have the same dimension, then there will be a kind of a mismatching dimension that you wouldn't be able to add anything to. So you'll see when we look at these examples. So if we look at part A, I'm going to write the dimensions underneath. We want to get in the habit of looking at these matrices and identifying exactly what the dimensions are, because it's going to be more and more important in coming sections. So this one has 2 rows, 2 columns. That makes this a 2 by 2 matrix. Remember, rows first, then columns. And then this one also has 2 rows, 2 columns. So this is a 2 by 2 matrix. So the dimensions are identical, which means we can add them together. So the way that adding these together works is, like I said, we're just going to match up the corresponding elements and add them together. So for this spot, we're going to add the 6 and the -3. So I know we can probably do most of this in our heads. I'm just going to write it out so you can see exactly where all these numbers are coming from. And then move over to this spot right here. So I'm going to add the first row, second column items here. Okay, so that'll complete my first row of my new matrix. Then I'm in the second row, first column, so I'm going to add the 2 second row, first column elements. -1 on the left, 0 on the right, and then second row, second column, I add those corresponding elements together here. Okay, so I'm just going to clean this up and I will have a new matrix. So 6 and negative 3 gives me 3, 4 and 1 is 5, negative 1 and 0, and 0 and 3. So that would be your final answer, that new matrix that you get. Okay, so now let's take a look at B. Part B, we've got 2 rows and 3 columns. So this is a 2 by 3 matrix. And then the next one has 2 rows, 2 columns. That makes this a 2 by 2. I made a very important note that they have to have the same dimension to add them together. So according to what I wrote down here, I shouldn't be able to add these. So you'll see why, because if you matched up elements, these two would add together, these two would add together, and then the 0 wouldn't have anything to add to. So if there aren't any elements here, people have tried to say that you could just add zeros, and that doesn't work. You cannot possibly add something to something that doesn't even exist. So you wouldn't be able to add these together. So as an answer for this, you could just say that it's impossible. It's not really that there's no solution necessarily, because you're not even able to go to the part where you would attempt to find a solution. So we just say it's impossible, there are mismatching dimensions, and so you can't even begin this problem. Okay, next thing we're going to do is multiply by a scalar. So a scalar is just a constant, so multiplying by a scalar, it's like you're taking an entire matrix A and you're multiplying it by a scalar. So quick little note here that K is a constant. So just a number, it can be positive, negative, whole number, fraction, doesn't matter. It's just got to be a constant. So you can't multiply it by a variable. We can't multiply yet by another matrix. We're just multiplying by a constant. So what we do is we multiply every single element by that constant. Okay, so let's take a look at our first example here. So we've got matrix A, and if we look, we've got 1, 2, 3 rows and 2 columns. So that is a 3 by 2 matrix. So that means that if I multiply by a scalar, it's still going to have the same dimensions. So when this says 2A, I am going to take this entire matrix and multiply every single element by 2. Okay, so 2A, I can put a 2 on the outside, copy down my original matrix here. So it's almost like a distribution idea. It's like I'm distributing that 2 to every single one of these elements. So multiply 2 by 2, I get 4. Multiply 1 by 2. Multiply negative 1 by 2. 2 times 3. 2 times 0, of course, is still 0. And then finally 2 times 5 is 10. So that would be my new matrix. It's got the exact same dimensions as my old matrix. All I did is I took every element in here and I multiplied it by 2. So that is scalar multiplication. So now we're going to kind of combine a couple of these things and look at properties of matrix operations. So it says we've got 3 matrices, A, B, and C. We've got matrix sum and product and a scalar K. So we've talked about how to add matrices together and how to multiply by a scalar. So we've got these 4 properties that will hold. The commutative property we learned about in chapter 1 with numbers, it holds for matrices as well. So the commutative property of addition means that you can add matrices together in any order and you would still get the same thing. Associative property of addition is basically the same as the associative property we learned in chapter 1. If you're adding 3 matrices together, you can group them in any way that you want. So the associative property is the grouping property, whereas the commutative property is an order property. Left scalar, the distributive property means if you multiply by a scalar on the left, you could just distribute that K, be K times A plus K times B. So that works, pretty much exactly the same as the distributive property with numbers worked. The weird thing with matrices is that sometimes we multiply by something on the right. So that's what I mean by the right scalar distributive property. So this would almost be like distributing in opposite order. We'd do A times K, so the K would technically be on the right, and then B times K. So again, the K would technically be on the right. For multiplication by a scalar, it all works the same, but in the future, with matrices, left multiplying could be different than right multiplying, and you'll see in the next section. So example 4 here, we want to find this. So we're going to do a combination of things. So 4A minus 3B. So we're going to find 4A. So 4 times this matrix that I have written up right above me for A. I'm going to distribute that 4, multiply every single thing by 4. So 4 times 2 is 8, times 3 is 12, 4 times negative 1 is negative 4, and 4 times 0 is still 0. So I got that. I just found 4a. Now I want to find 3b. Okay, so I'm going to take 3, I'm going to multiply by negative 2, 1, 0, negative 1. I'm just taking these elements from this matrix right here, and I'm going to multiply everything by 3. So 3 times negative 2, 3 times 1, 3 times 0, and 3 times negative 1. So that is my new matrix. That is 3b, so now I can find this. So notice, this is a 2 by 2 matrix, 2 rows, 2 columns. This is a 2 by 2 matrix, which means that they're the exact same dimension, so I'm able to add them together. I guess in this case I'll be subtracting them. So here's 4a, and then minus 3b. Okay, so when we're subtracting, we're going to be super careful, so I'm going to write all the work out. So 8 minus negative 6, we're just subtracting corresponding elements. And then the next element is 12 minus 3. Down bottom left, negative 4 minus 0, and 0 minus negative 3. Okay, so be super careful with the subtraction. Notice, of course, every time you see minus a negative, it turns into plus a positive. So let's simplify down. We've got 8 and 6 gives us 14. 12 minus 3 is 9. Negative 4 minus 0. And 0 plus 3. So that is your new matrix. We did a combination of scalar multiplication as well as subtraction. Okay, so last one here. Small company makes unfinished desks and cabinets. Each item requires different amounts of hardware shown in the matrices. Company has orders for 3 desks and 4 cabinets. Express the company's total needs for hardware in a single matrix. All right, so 3 desks and 4 cabinets, and is basically like an addition thing. Okay, so express the company's total needs. So if we take this whole thing and multiply it by 3, all of the individual, like here are the short nails, short screws, long screws. If I multiply everything by 3, then it'll give me all the hardware that I need for 3 desks. Same thing with the 4 cabinets, and then when I add together, I'm adding the short nails for the desk plus the short nails for the cabinet. The resulting matrix will give me the total number of short nails that I need. So 3D, so we can write this all out like this. Here's D plus 4C Okay, so let's start with the multiplication. Think order of operations. The multiplying has to happen first. So take this matrix and distribute the 3. So 3 times 10, 3 times 6, 3 times 8, and 3 times 4. So that's how many total individual, screws, nails that I need for the desks, all 3. And then I'm going to multiply this matrix by 4. 4 times 4, 4 times 8, 4 times 3, and again 4 times 4. So that's all the hardware I need for the 4 cabinets. So now I'll combine them and I'll get the hardware that I need all together. So first I'm going to add these. 30 plus 16 gives me 46. So 46 is the total number of short nails that the company will need for this order. 18 plus 32, that gives me 50. So 50 is the total number of long nails that they need. 24 plus 12, 36 total short screws, and then 12 plus 16 gives me 28, which is the total number of long screws that they would need. So here's the matrix, and this is like I was saying in the previous video, when you're dealing with story problems, each element has a very specific meaning. So, all right, I believe that's it. So next we'll be multiplying matrices together.